Last but not least, we've got our final type of transport that we're going to be talking about. And I'm still on page 53. But the last type of transport we're going to talk about is osmosis. And osmosis is important. It is only for water. So it is the movement of water. And it gets a little bit tricky. So now it still has to do with concentration gradients. But now we're talking about a solute concentration. So the solute is the thing that is dissolved in the water. So you're going to go from movement of water from areas of low solute concentration to areas of high solute concentration. And it works through a semi-permeable membrane. So I just threw a bunch of things at you. I'm going to draw a diagram. I'm hoping this will help. So, a semi-permeable membrane, like your cell membrane, means that some things can pass right through, but other things cannot. So, something like a salt ion might not be able to pass through the membrane, but water would be able to pass through the membrane. Or glucose, a really large molecule, might not be able to pass through the membrane, but the water is able to pass through the membrane. So there are three sort of setups that we often talk about. Move that up. So I'm going to draw three boxes. And then in each of these, I'm going to draw just a very simple cell. And what I'm going to change is the concentration. So what I am drawing is the solute. It's the thing that's dissolved in the liquid. So let's imagine that this is sugar water. It's got glucose dissolved in the water. And in my first example, I'm going to have a whole bunch of that sugar inside of the cell. So this has got my semi-permeable membrane. So water is going to be able to transport itself through the membrane, but my glucose cannot. Now, I could have some glucose outside of the cell. The cell is in a solution, so it doesn't dry out. So I've got some glucose inside of the cell, I've got some glucose outside of the cell, but I've got way more glucose in the cell than I do out of the cell. Now the glucose can't move. So instead, the water is going to move. And the water is going to try and make it so that these glucose molecules are just as spread out as these glucose molecules. It's going to try and even this out. Well, the only way to do that is to actually take water and move it into the cell. Because if the water moves into the cell, then the cell will start to spread out, and there will be more space between these glucose molecules. The cell will be taking up more of this space, which means there will be less space between these glucose molecules, and it will start to even out. So in this case, water moves into the cell. Let's look at another example. We'll have a lot of water moving in. In my other example, we're going to have the same amount in terms of concentration of glucose inside the cell as outside the cell. So here's actually a really good example of what I mean when I say concentration. When I say concentration, I'm not talking about how many glucose there are, because as you can see, I already have way more glucose outside of the cell than I do inside of the cell. The trick is that the glucose is about the same space from each other outside of the cell as they are inside of the cell. Now, yes, some of them are a little bit closer and some of them are further away, but overall, these are about the same concentration because the molecules are about the same distance apart from each other. They have the same sort of density, if you know what that is. Now, in this one, you're going to get some water moving into the cell, and you're going to get some water moving out of the cell. So this is going to be happening because you do have water moving into the cell and water moving out of the cell sort of at all times. However, in this instance, there is no net movement of water. So for every water molecule that moves in, a water molecule will move out because this is already at equilibrium. All right, last example, we're going to have a low concentration inside of the cell and a high concentration outside of the cell. So this is the reverse of the first picture. And if it's the reverse of the first picture, and you know that these glucose molecules are trying to get evened out, but the only thing that can do the moving is the water, make a guess as to which direction the water is going to move. Is it going to move into or out of this cell? I'm going to draw lots high concentration here, lots of glucose. Okay, so in this one, what's going to happen is the water is going to move out of the cell. If we have water moving out of the cell, then the cell will shrivel up. And if the cell shrivels up, these glucose molecules are going to get pushed closer together. At the same time, there's going to be more water out here, so these glucose molecules can spread further apart. So in this one, my H2O moves out of the cell. So when I say that it moves from low solute concentration to high solute concentration, the solute is that glucose here. So here we've got water moving from an area of low solute concentration, there's not much glucose, to the area of high solute concentration. Here there's a lot of glucose. There's another bit of vocabulary that you need to know about this, and that comes from the words hyper, hypo, and iso. So have you heard of tonic water before? So tonic can refer to the water or the solution. And then we've got some prefixes. We've got hyper, hypo, and iso. Oh my goodness, my light's turned off. Come on, lights. Okay, If you are hyper, do you have a lot of energy or a little bit of energy? If you're hyper, you have a lot. So hyper means more. Hypo, like when you're hypothermic, it means you have less heat. So hypo means less. And iso means equal. So we often refer to the solution that the cells are in as being a hypertonic solution, a hypotonic solution, or an isotonic solution. So let's talk about what that means in terms of this setup here. So here, the cell is in a solution that has less concentration of glucose. So we would say that this solution is hypotonic. There's less glucose than inside of the cell. So the cell is hypertonic to the solution. Here, my cell and my solution that the cell is in are isotonic. They have equal concentrations. Here, we would say that the solution is hypertonic, the cell is hypotonic. So because these words mean more and less, they have to actually refer to something else. So it's always a relationship between one thing or the other thing. So oftentimes it's the solution that we're talking about. So this would be a hypotonic solution. This is an isotonic solution. And this is a hypertonic solution. So you should be able to tell me which way water will move into or out of a cell if it's placed in a hypertonic solution, an isotonic solution, or a hypotonic solution. And that's all.